So there's Bayes' theorem. Let's say we're interested in parameter theta that might represent the probability that a randomly selected person would be right-handed. We can begin with some prior beliefs about what this value of theta would be. We can collect some data, and then ultimately what we arrive at is our goal, the posterior distribution of theta. And up until now, we've seen 3 different ways to calculate the posterior distribution of theta. The first deal was grid approximation, created a very fine grid of 200 different values of theta, assigned prior probabilities of those. In the water tossing or in the globe tossing experiment, we had y is equal to 4, n is equal to 10. We did the algebra and arrived at our posterior distribution. An alternative approach is to use conjugate priors, conjugate pairs. So we've got a binomial likelihood function. Its conjugate prior would be a beta distribution. And we know that if the prior is a beta distribution with parameters a and b, and we observe y successes in n trials, then we can immediately, automatically, and exactly calculate our posterior. It's going to be a beta distribution as well with parameters a star and b star, where a star is equal to y plus a, and b star is equal to n minus y plus b. And thirdly, last week we saw the Metropolis algorithm. So the whole idea behind the Metropolis algorithm is that this denominator is very difficult to determine. So we'll just get rid of it, change that to proportionality sign, and go on a Markov chain Monte Carlo random walk through this. So we had the Metropolis algorithm that's shown right here. And the concept of an algorithm is just that it's a series of steps that is designed to obtain some goal, which in this case was the posterior distribution. We had Markov chain Monte Carlo by hand, the R program that's on E-class. We implemented this algorithm. We produced this probability distribution shown as a bar plot, and quite delightfully, it had the same shape as that which we obtained through our conjugate prior. In practice, however, we're not going to use any of those 3 different methods. In practice, what we're going to use are R packages. And the particular R package that we're going to focus on is runjags. And this week, what we're going to do is we're going to implement Bayesian data analysis with runjags. And the program we're going to use is first program binom R. So this week really has a couple of goals. First is to give you this package that you can use as a starting point if you want to do Bayesian data analysis on your own data. The second and more important purpose is to go over some vocabulary that you're likely to encounter if you're reading papers that use Bayesian data analysis. So this is an introductory video, and there's a couple things I want to go over. And the first is some terminology surrounding algorithms, languages, and packages. Algorithms, languages, and packages. So, last week, we did the Metropolis algorithm. And the Metropolis algorithm is simply an example of a specific case of the Metropolis-Hastings algorithm. And if we think about the Metropolis algorithm, it includes Gibbs sampling, which is another algorithm which is a lot more efficient than the Metropolis algorithm when there exist multiple parameters. So we've got these algorithms, and these are the steps that we use to get some sort of a goal, which in this case is to calculate the posterior. But we need to communicate with a computer, and we communicate with the computer with some sort of a computer language. In the case of Bayesian data analysis, we're going to think about these as being probabilistic programming languages, or PPLs, because we're dealing with probabilities, we're dealing with distributions. Now, if we're going to use as our algorithm a Gibbs sample, there's a couple languages that are appropriate for Gibbs sampling. One is bugs, Bayesian inference using Gibbs sampling. Another is DAGs, just another Gibbs sampler. So these are the languages. I want to use these languages, but I want to use them within the R environment because I really like RStudio and the other features of R. So what R has are packages. So R's got some packages, and I've rather arbitrarily divided these packages into two groups: code-based packages and formula-based packages. And an example of a code-based package would be runjags. And the reason it's called code-based, if I look at the syntax of runjags and the syntax of jags, they're essentially the same sort of thing. And I will tend to use runjags and jags. I'll go back and forth between them. There really isn't much of a significant difference between them. Code-based, fairly complicated code is involved. In contrast, there are formula-based packages in which one only oftentimes needs to provide a very simple formula. An example of that would be Barral. So there's many different ways to do Markov chain Monte Carlo. And what we have on this side of the line is one family or group of algorithms. On the other side of the line, what we have is another group or family of algorithms. An example would be the Hamiltonian Monte Carlo that includes this thing called NUTS, which is no U-turn sampling. The programming language that would be used to implement NUTS would be called Stan, and that's named after Stanislaw Ulam, who did a lot of early work on Monte Carlo approaches. If we compare JAGs, which is what we're going to be using, with Stan, JAGs was really popular from about the 1990s, maybe to the 2010s, and Stan is more recent. However, I decided to go with JAGs. The reason for going with JAGs is that it uses the Metropolis algorithm, which is perhaps the simplest of all algorithms, which makes it really appropriate for an introductory seminar such as this one. In terms of our code-based packages, there's this thing called R2Stan, and in terms of our formula-based package, for Stan, we've got this thing called BRMS. And in week 8, I'm going to go over in some detail BRMS. Second thing I want to talk about is autocorrelation. And this week we're going to look at the program, first program binom.r. We're going to use the runjags package. The probabilistic programming language is going to be JAGs. And we're going to go on a Markov chain Monte Carlo random walk. And as a consequence of going on a random walk, that's going to induce autocorrelation, and that's going to cause the sampling efficiency to be reduced. There's more detail on E-class in this supplementary material, but right now I just want to go over some of the basics. I'm going to do that by example. So here we have fields, and these fields have high fertility and low fertility areas, and we're going to sample them in two different ways. One is a fully random sampling scheme, and another is a random walk. So in the fully randomized scheme, we could use something like GPS, and every point on the field would have an equal probability of being sampled. With a random walk, we start off at some point, and then we've got an algorithm that tells us, okay, we're going to move a certain direction, a certain distance, and then do that again, and do that again. So with fully randomized sampling, it's highly efficient because each location in the field has an equal probability of being selected. On the other hand, with a random walk, that's not the case. So the probability of this point being selected is determined in part by where it was at the previous time interval. And because of the fact that it's not random, what you get is a reduction in efficiency, because you can see what's happening here is that just by chance, because of the constraints imposed by random walk, the observations have been concentrated on the high fertility part of the field. And so, as a consequence, if we look at both of these fields, we've obtained 8 samples here and 8 samples here. But the effective number of samples, I'm just going to make some numbers up. I'm just going to make a number up. We might say that the amount of information contained in these 8 samples taken via a random walk, because of the reduction in sampling efficiency induced by that random walk, might be the equivalent, again, just making up a number, of 6.4 samples obtained through a fully randomized sampling design. So the whole idea is we go on a random walk that induces autocorrelation, and as a consequence of autocorrelation and a reduction in sampling efficiency, the effective sample size can be reduced. So again, in our example, we're saying that the effective sample size is reduced from 8 to 6.4 because of the autocorrelation. So the third thing I want to talk about are directed acyclic graphs, or DAGs. And here we have an example of a DAG, and it's obviously a graph. It's directed, and it's got an arrow here and an arrow here, and it's acyclic because there are no cycles, there are no feedback loops. And these directed acyclic graphs are going to be really helpful in that they're going to help us visualize components, the variables, and the relationships among those components and variables, and that's going to help us with writing a runjags code. So here we have an icon that represents the likelihood function. So there's one component. It's going to be a binomial, and another component is this icon that represents the prior, and it's going to be a beta. In terms of interpreting our directed acyclic graph, a good way to begin is at the bottom. So we're going to start with, and we're dealing with the handedness experiment, we're going to have y is equal to 9 successes, and these y is equal to 9 successes were deemed to have arisen. That's why we've got these arrows. These 9 successes arose from a binomial distribution with parameter theta that's our objective interest, and n is equal to 10 observations. Sitting beside this arrow, we've got a tilde sign. Sitting beside this arrow, we also have a tilde sign. Tilde signs reflect the fact that these arrows involve values that are associated with distributions. In other words, there's stochasticity involved, and that's what's implied when you see these tildes. In week 7, next week, when we go over hierarchical models, instead of having tildes, what we're going to have is equal signs for those variables that don't arise stochastically from distribution, but rather arise deterministically. Now we can think about this arrow, and this arrow reflects the fact that the prior for theta is a beta distribution with these parameters. Once we've got this DAG set up, once we know the components and the relationships among them, that facilitates the writing of our runjags code, because these arrows are both going to translate or need to be translated into code. So we've got this arrow here that reflects the fact that the prior for theta is a beta 4.2. When it comes time to writing our runjags code, we're going to write theta is distributed d beta 4.2. And as a consequence, as runjags goes on its random walk, for each value of theta, it can determine the prior probability of theta. You might be wondering why I use a symbol here and the word here. Well, typically, we use symbols, but if we're writing code in runjags, then we need words, and it just seemed to me that a good word for the symbol theta here would be the word theta there. If we think about our likelihood function, we've got these y is equal to 9. We're going to keep the data constant at y is equal to 9, n is equal to 10, and as runjags goes on its random walk, it can calculate the posterior probability of theta conditional upon the data for each different value of theta. So the whole idea is that these directed acyclic graphs allow us to easily visualize the components, the variables, the relationships among them, and that's going to facilitate the writing of runjags code.